All right, so in this video, we're going to continue verifying the trig identities that we are given. So starting with part A here, we have a fraction, and we're trying to prove that this fraction is equivalent to cotangent over cosecant. So the first thing I notice when I'm looking on this side here, so we're always trying to prove that the left-hand side is equal to the right-hand side. So I like to always play with the left-hand side to try to manipulate it to make it look like the right-hand side. And the first thing I notice is that the numerator has a cosecant squared. And anytime I notice a trig function with a squared, I'm thinking perhaps I need to use the Pythagorean theorem. So the Pythagorean theorem for the one that has cosecant says that if you have 1 plus cotangent, this will be equal to cosecant squared. So because I have one that has a minus sign that's with it, if I were to move this minus sign over, if I were to just subtract this minus sign off, that means that cotangent squared is equal to cosecant minus 1. So I can say all of this is actually equal to cotangent. So that's what I am going to claim. And then the bottom is just going to be cosine. Now from here, I'm thinking it still doesn't look like that side. So I still haven't proven that these are actually equal to each other. So I keep going. I'm thinking, okay, cotangent is really cosine, or actually, my bad, I didn't mean to write theta. Should probably write an x here. So cosine over sine. So what I've done is change the cotangent to cosine over sine, and I squared the top and bottom since it's a cotangent that's being squared. So I've rewritten it as a fraction in terms of sine and cosine. Now from here, I'm also dividing by cosine, so that means that I need to multiply it by its reciprocal, which would be 1 over cosine. So if you think about this cosine as cosine over 1, remember if you're dividing by if this is going to be a fraction and you're going to be dividing by a fraction, you need to flip the fraction. So that's why it's 1 over cosine. Now from here, I start to notice that the cosine will cancel out on the top and bottom, but you still have a cosine left in the top. So now I really have cosine to the first power on the top and then sine squared on the bottom. Now, looking at this here, I have a cotangent here and a cosecant here. So maybe what I need to do is think about separating the sine so I can get cosecant, because cosecant is basically sine in the denominator. So if I separate this as cosine and separate the sine in the bottom like this, so what I've done is sine times sine is still sine squared. So I've split up the denominator, the square, into 2 sines. So I can use this one with the cosine that's on the top. And cosine over sine is just cotangent. And then 1 over sine is cosecant. And finally, I've made the left-hand side look like the right-hand side. And I'm done. All right, so this next one here, I have basically a very similar idea. What I notice is the top here has a secant squared minus 1. So I'm thinking, okay, this might be a Pythagorean theorem. So I'm going to bring out my Pythagorean theorem for secant. So anytime you have tangent plus 1, that's going to equal secant. If I were to subtract over the 1, this would be tangent equals secant theta minus 1. So secant squared minus 1 is equivalent to tangent. So what this means is this top here is equivalent to tangent. In this case, not theta, but tangent x. Which is getting me closer to this answer because there is a tangent here. So I might be getting closer. So I have a tangent x over sine x. Now from here, it looks like I'm taking tangent and dividing it by sine. So perhaps I need to manipulate tangent in terms of sine and cosine so I can try to cancel things out. So like what I did before, I'm going to try to write tangent in terms of sine and cosine. So that would be sine squared over cosine squared. I need to square them because this is a tangent squared. And then what I'm going to do is take the sine that's here. And remember, that sine is technically over 1. And so I need to flip it because I'm dividing by sine. So this is going to be 1 over sine. Now, when I do this, I start to realize, oh, okay, the signs cancel out, at least one on the top and bottom. And so I'm left with sine on the top, just this sine times 1 is just sine, cosine in the bottom. But it's a cosine squared. So again, I'm thinking, okay, maybe I need to separate this cosine into 2 cosines in the top and bottom. So cosine times cosine gives me cosine squared. Since I was able to separate it, I can see that sine over cosine is actually just tangent, and 1 over cosine is secant. And voila, we now have made the left-hand side look like the right-hand side. And we are done. So what I like about these problems more than I like the problems that we did in the first lesson is that there is a stopping point. You know that you're done proving when the left-hand side looks like the right-hand side, which is kind of nice. All right, let's try out a few more problems on the next page here. So for part C here, we have a fraction, and this one has a sine in the bottom, and this one has a cosine in the bottom. So the first thing I'm thinking of is joining them together by finding a common denominator. Because what I noticed on the other side is that there's no fraction, and so I probably need to combine these in some way. So first off, I'm thinking common denominator. So I have a sine on this side and a cosine on this side. So I'm going to start by multiplying the left side by cosine of A, and then I'm going to need to multiply the top by cosine of A as well. So I'm going to multiply this side by sine of A to make the top and bottom basically the same denominator. So I'm declaring that the denominator both be cosine sine. Once I have done that, I can join them together as cosine and sine. So I'm already joining them together because they're going to end up being the same anyways. I'm going to bring down that minus sign. I'm going to multiply these two together. So that would end up being cosine of A secant of A. And then this one is going to be sine times sine, which is going to be sine squared A. Now from here, let's focus just on the top for a moment. Like this is a cosine and this is a secant. So those two are actually reciprocal of each other. So if I just focus on this point right here, this is going to be cosine times secant, and secant is just 1 over cosine. So I'm changing secant into its reciprocal identity in terms of cosine because I'm trying to cancel out stuff. And I'm going to bring down everything else just the way it is. Bring down the denominator. So when I change this here, I notice that cosine does cancel out top and bottom. So I'm left with just a 1. So this ends up being just 1 minus sine squared on the top, and then cosine of A, sine of A on the bottom. And this is kind of nice because, again, I notice there's a 1 minus sine squared. So this here is the Pythagorean theorem. 1 minus sine squared is cosine. So this is equivalent to cosine squared. And so I have a cosine squared on the top, and I have cosine A and sine A on the bottom. All right, now that allows me to cancel out some more because I have a cosine on the top and I have a cosine on the bottom. So I can cancel out one of my cosines on the top, and this is now cosine A over sine A. All right, cosine over sine is just cotangent. All right, I can't really do much anymore. And voila, I actually got the left-hand side to equal the right-hand side. So both sides do end up equaling cotangent. Okay, so that one was quite a loop there. Let's try out this one here. So this one has a lot going on as well. The first thing I notice is that it's being subtracted two fractions. So I probably want a common denominator because I do need to join them because I only have one trig function here. So that tells me that at some point these had to have joined to have gotten tangent. So the one thing I noticed is that this one already has a sine, so it just needs a cosine to be multiplied to make that same denominator happen. So I'm going to multiply the bottom by cosine and then also the top by cosine. And so this gives me 1 over sine x cosine x. And this is also going to be sine cosine x. So I'm just going to bring the denominator together. Actually, let me just shift that just a little bit. So I'm going to write this as 1 minus cosine squared on the top, and then the bottom be sine x cosine x. So what I've done is brought the denominators together and also the numerator. So I have 1 down, negative sign, and cosine times cosine is cosine squared. So I've kind of joined everything together. And then I notice again that the top here is 1 minus cosine squared. And anytime you have a 1 minus cosine squared, this is equivalent to sine squared because of the Pythagorean theorem. Anytime you subtract over cosine and have a 1 in front, this is going to end up being sine squared. So this will be sine squared on top and then the sine and cosine on the bottom. So that allows me to cancel out the sine that's in the bottom with one of the sines on top. So I'm left with 1 sine on the top and 1 cosine on the bottom. So sine over cosine is just tangent. And so finally, the bottom here is actually equal to the right-hand side. All right, so our next problem here is this one, part E. I'm going to have to erase this floating problem. So this one we have, it looks like these two end up adding to give me 1. And that's kind of hard to see. So the first thing I'm thinking of is either finding a common denominator or manipulating these cosecants and secants in terms of sine and cosine. So what I notice first is that this is sine and this is cosecant. If I'm going to divide them, they're going to end up being reciprocals of each other. So there definitely is going to be some cancellation. So because I can notice this is right away that these are reciprocals of each other, and so is secant is reciprocal to its numerator cosine. Because I notice that they are reciprocal, I might not try to find a common denominator. I might just try to simplify each fraction separately. So here's what I mean. I'm going to take the sine here, drop it down. And cosecant is just, when you think about it, it's just 1 over sine. So if you're dividing by 1 over sine, you're going to have to flip this fraction. So this is going to end up being sine over 1. Now, I'll take care of this later, but I'm bringing down the plus sign, bringing down the cosine, that's in the numerator, and secant is actually 1 over cosine. But if you're dividing by this 1 over cosine, this is going to flip. So this ends up being cosine over 1. And so when I do this, I start to realize, oh, sine times sine gives me sine squared. Bring down the plus sign, and cosine times cosine is cosine squared. And so that's lovely. Anytime I have sine squared plus cosine squared, it actually just equals 1. So I did get the left-hand side to match up with the right-hand side. So that's kind of nice. All right, so this one also happens to be a very similar problem to where you also end up getting 1. But looking into this here, I notice I have a cosecant. I have a cosecant here. There's many ways to do this problem. You could start this problem by changing everything in terms of sine and cosine. You can try to factor out cosecant, whatever your heart desires. Now for me, I think I'm going to just start with something simple and just change them all in terms of sine and cosine. So like cosecant here is just sine squared. I can change that to 1 over sine squared. Cosine I'm not going to change since it's already in cosine form. Cosecant, I'm going to change it to 1 over sine squared. When I do this, I start to realize that these two would end up being on top of each other. So this would end up being cosine squared minus or over sine squared. And this is 1 over sine squared. So they both have the same common denominators, which is kind of lovely because you can write this as 1 over cosine squared for the top and bring the numerators together because the denominators are the same. And you can make the denominators just as 1 now. So I've joined basically the numerators together and written this as one fraction. So I'm getting closer to having this as one term. The next thing I noticed is that the top here is 1 minus cosine squared. Anytime you have 1 minus cosine, you have a sine squared. So I know that because I'm using the Pythagorean theorem. So if this ends up being sine squared for the top, and the bottom is already sine squared, then sine squared over sine squared is just 1. And so finally, I have this left-hand side to match up with the right-hand side. All right, so for this next problem, I'll go ahead and do very similar to the last two problems here. I'm going to see if I can manipulate them in terms of sine and cosine. So that's kind of like my basic strategy, is if I can manipulate them in terms of sine and cosine, I'll try to do that. If I can't, then I'll use some sort of other identity. So like tangent is sine squared over cosine squared, since this tangent is squared. I have a cosine that's next to it that I'll drop down. So now I'm trying to prove that all of this equals 1. And the first thing I notice right away is that these cosines cancel each other because they're diagonal. So then I notice all I have left is cosine squared plus sine squared. And cosine squared plus sine squared, even though it's in a different order, it's just equal to 1. And so I've proven that they are actually equal, and you can use that as an identity. Okay, last but not least, we have this problem here. And this one, it gets a little bit tricky. So when I first see this problem, I notice that they're both raised to the 4th power, and there's a minus sign here. So I'm thinking, like, I can't combine these two because this one's a cosine, this one's a sine. I can't really use any identities here because these are kind of already simplified too. Like, they're both sine and cosine. And, thinking about it, I noticed that their exponents are both to the 4th power, and there's a minus sign. So I'm thinking this could be a factoring problem. So if I were to use factoring here, let's make some room to write. This does have a minus sign, and sine squared is a perfect squared, and so is cosine squared. So if I make cosine maybe a 2 as an exponent, and this one a 2, and then the sine as a 2, and the other sine as a 2, maybe make this one a negative and this one's a positive, I might get somewhere. So cosine times cosine squared gives me cosine to the 4th power, and sine squared times sine squared, they're both sine squared, so this would be sine to the 4th power when I multiply, and this one's a negative, this one's a positive, so when I multiply, I should get a negative. So this works. Notice that if I multiply the middle terms, sine squared times cosine squared is a negative. If I multiply the outer, that's a cosine squared times a sine squared, so they would end up canceling the middle term. So I've factored this out, and this is still the same thing, just factored out. And I'm thinking, okay, maybe I can try to add these two together, because if I add these two together, cosine plus sine squared is just 1. So if this is just 1, 1 times that is just itself. So now I just have cosine x minus sine squared, right? And then the next thing I'm thinking about is, that still doesn't look like that side. Notice how this is all in terms of sine. So maybe I need to change this cosine in terms of sine. And that's where I start thinking about the Pythagorean theorem again. So the Pythagorean theorem says that if you have sine squared plus cosine squared, you can try to move over something to try to get the cosine squared by itself. So what I'm going to try to do is replace cosine squared in terms of sine. And so if I want to get this cosine by itself, I have to subtract over the sine squared to both sides. So that would cancel. And so I really have cosine squared that's left behind, 1 minus sine squared. So cosine squared is equivalent to 1 minus sine squared. So I can replace all of this with what it equals, which is 1 minus sine squared. Now, bringing down the minus sine squared that's to the right of it, I start to notice that these two are common, right? This one both has like a -1 in front, a -1. So if I combine them, bring down the 1 that's in front, minus -1 minus 1 is -2 sine 2x. And now this finally looks like the right-hand side. So I am finally done. All right, that is it for the video. I hope you guys found this helpful. If you have any questions, feel free to email me. Bye, guys.